In this episode, we're going to focus on a threat pattern that surprises beginners the first time they see it in cloud investigations. Attackers do not only break in, they try to stay in. In serverless environments, staying in can look different than it does on a traditional server because there is often no long-running machine to plant a classic backdoor on. Instead, attackers aim for persistence through configuration, code, and identity, because those are the pieces that keep working even as compute instances appear and disappear. Reinfection is the attacker's ability to come back after you think you cleaned up, often by abusing your deployment process or hidden trust paths. Silent reuse is when attackers keep using the same access path or stolen credentials in ways that blend into normal function execution, sometimes for weeks. The goal here is to harden serverless functions so that even if an attacker touches one function, it is difficult for them to remain, return, or operate quietly. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A practical way to approach this topic is to stop thinking of persistence as something that requires a permanent machine and start thinking of persistence as something that requires a durable control point. In serverless, durable control points include function code packages, shared dependencies, event triggers, identities and permissions, and the control plane settings that define how everything connects. If an attacker can modify a function's code, they can add logic that quietly exfiltrates data whenever the function runs. If they can modify a trigger, they can cause their code to run on a schedule or on a specific event, even if no user is directly calling the function. If they can create a new privileged identity, they can come back later and reconfigure resources even after the original compromised account is disabled. The hardest part is that these changes can be subtle because serverless systems are designed to be changed and redeployed frequently, which gives attackers cover. Hardening is about making those durable control points narrow, monitored, and resistant to silent changes. It helps to begin with the simplest persistence mechanism, changing function code in a way that looks like a normal update. A serverless function is code plus configuration, and code changes are expected in healthy engineering cultures, so attackers try to hide in that normal churn. A tiny change, like adding one outbound call or adding one extra write to a log-like storage location, can become a covert channel for data theft. Another subtle pattern is modifying error handling to leak information only under certain conditions, which reduces the chance of being noticed in routine testing. Hardening against code-based persistence starts with treating code updates as security events, not just delivery events, because production code defines production behavior. You want clear accountability for who can update functions, and you want changes to be reviewable and traceable so that surprise edits do not slip in during busy periods. The key beginner lesson is that in serverless, code is an attack surface and also a persistent surface because code runs repeatedly and automatically. Reinfection often happens when teams clean up the visible symptom but leave the upstream source untouched, and in serverless that upstream source is frequently the deployment pipeline. Continuous integration and continuous delivery, CI/CD, is the common term for automated build and deployment workflows, and if attackers gain access to that workflow, they can reintroduce malicious code every time you redeploy. This is a particularly frustrating pattern because it can look like the environment is haunted, where you fix a function and the same behavior returns days later. Hardening here means you treat the pipeline and its credentials as high-value assets, because they can write directly into production. You also reduce the number of identities that can deploy, limit what those identities can change, and ensure deployment actions are logged and reviewed. Even without describing specific tools, the principle is clear. If the path that creates your functions is compromised, then your environment will keep producing compromised functions. Blocking reinfection requires securing the factory, not just cleaning the product. Another major persistence pathway in serverless environments is the manipulation of event triggers, because triggers decide when code runs and what data it receives. Attackers who can add a new trigger, broaden an existing trigger, or redirect an event source can create reliable execution without needing to expose a public endpoint. A scheduled trigger can run a function quietly at low volume, making it blend into background automation. A storage-based trigger can be abused by placing specially crafted objects that cause the function to run in a controlled way, which can be used to probe for weaknesses or to activate hidden behavior. Hardening triggers means narrowing who can create and modify triggers, narrowing who can write to the event sources that feed triggers, and narrowing the function's permissions so that trigger-driven execution cannot do more than intended. You also want trigger changes to be treated like permission changes, because they effectively change the environment's behavior boundary. The beginner insight is that triggers are a form of remote control, and remote controls must be locked down. Silent reuse is often powered by identity misuse, because attackers prefer to keep using credentials that already work rather than constantly breaking new things. In cloud environments, identity and access management, IAM, determines what identities exist and what they can do, and serverless functions often run under service identities that are powerful enough to touch sensitive resources. If an attacker steals a token or compromises a function that holds a privileged identity, they can reuse that access repeatedly in ways that look like normal function activity. This is especially dangerous when many functions share the same identity, because the attacker's access becomes widely useful and harder to attribute to one compromised component. Hardening against silent reuse starts with least privilege, but it also includes narrowing where and how identities can be used, such as restricting administrative actions, requiring strong authentication for sensitive control plane changes, and monitoring for unusual patterns of privilege use. The practical beginner takeaway is that if identities are broad and shared, attackers can hide inside normal service calls. But if identities are narrow and unique, misuse stands out. A strong serverless hardening strategy also focuses on limiting the ability to create persistence through new identities or new access grants, because that is how attackers turn a temporary foothold into a long-lived presence. If an attacker can grant themselves additional permissions, they can reduce the need to keep re-exploiting the original weakness. If they can create a new privileged role and assign it quietly, they can survive credential resets and even survive function redeployments. This is why control plane permissions around identity management are among the most sensitive permissions in a cloud environment, and why separation of duties matters. Hardening here means that few identities can change roles, few identities can modify security-critical settings, and those actions are heavily logged and watched for anomalies. It also means that permission grants should be scoped, reviewed, and time-aware, because permanent broad grants are exactly what persistence needs. For beginners, the main idea is that attackers do not always need to hide in code if they can hide in permissions, because permissions can quietly authorize them forever. Serverless reinfection can also be driven by dependency contamination, which is a risk that grows as teams reuse common libraries and packages across many functions. Functions often package third-party libraries to move fast, and if a library is compromised or replaced with a malicious version, that malicious behavior can spread across dozens of functions in one deployment cycle. This is reinfection at scale, because even if you remove a malicious change from one function's code, the same dependency can reintroduce the behavior when the function is rebuilt. Hardening against this means treating dependencies as part of the function's trusted computing base, not as invisible plumbing. It also means controlling how dependencies are sourced, ensuring changes to dependencies are reviewed and traceable, and reducing the number of unnecessary dependencies that expand the attack surface. The key is not to fear dependencies, but to manage them deliberately, because every dependency is another place attackers can hide. Beginners should recognize that reinfection often comes from shared components, because shared components allow one compromise to spread quietly and repeatedly. Persistence and silent reuse also benefit from weak observability, because attackers want to operate in places where nobody is watching. Serverless environments can generate rich logs, but those logs are only useful if they include the right context, are retained long enough, and are protected from tampering. Hardening for this topic includes ensuring that function invocations, trigger events, permission changes, and deployment actions all produce auditable records. It also includes monitoring for patterns that suggest persistence, like a function that suddenly begins making outbound calls to unfamiliar destinations, or a function that runs on a schedule nobody recognizes. Another strong signal is a new trigger or configuration change that appears without a clear change request, because persistence often begins with small configuration edits. For beginners, it is important to see that detection is part of hardening, because preventing persistence is not only about blocking every change, it is about noticing and validating changes quickly. When visibility is strong, attackers have less time to establish durable footholds without being discovered. The concept of immutability is also useful in serverless hardening because it encourages you to treat running functions as artifacts that should not be modified casually or silently. In traditional systems, attackers often modify files on disk, but in serverless, the comparable attack is to modify the deployed code package or its configuration in the control plane. A hardened environment makes those modifications difficult for unauthorized actors and easy to detect when they occur. This is where infrastructure as code, IAC, becomes relevant as a concept, because defining function configuration and triggers in repeatable definitions makes changes reviewable and reduces ad hoc edits. The idea is not that everything must be perfect, but that changes should flow through a controlled path that produces evidence and consistency. When changes are controlled, you reduce both accidental drift and attacker-driven persistence, because there is less opportunity for silent edits. Beginners should remember that attackers love environments where changes are frequent and informal, because that is where malicious changes can hide. Another angle that matters for blocking reinfection is designing a clean separation between development, testing, and production, because serverless makes it easy for code and configuration to move quickly between environments. If development identities can deploy to production, or if testing triggers can reach production data sources, then a compromise in a lower environment can become a compromise in production with very little friction. Hardening includes separating permissions by environment, separating triggers and event sources by environment, and ensuring that production functions do not depend on resources that are writable from less trusted contexts. This kind of separation reduces reinfection risk because it prevents malicious changes from flowing upstream unintentionally. It also reduces silent reuse risk because tokens and identities from lower environments should not be valid in production contexts. For beginners, the lesson is that environment separation is not only about quality assurance. It is a security boundary that blocks attackers from turning an easy compromise into a valuable one. When environments are cleanly separated, you gain time to detect and correct issues before they reach the most sensitive systems. You also want to harden serverless functions by limiting what they can do when something goes wrong, because attackers often exploit error conditions and edge cases to trigger unusual behavior. If a function handles untrusted inputs and its error handling leaks internal information, attackers can learn about resources, permissions, and configuration, which helps them craft persistence mechanisms. If a function fails open, meaning it proceeds with an action even when validation fails, attackers can push it into risky states. Hardening includes careful input handling, consistent authorization checks, and safe error behaviors that do not reveal sensitive context or perform unintended actions. It also includes preventing functions from writing sensitive data into logs, because logs can become an exfiltration channel if they are accessible broadly. Beginners should see this as a practical extension of application security, where the goal is predictable behavior even under malicious input. When functions behave predictably, attackers have fewer opportunities to turn unusual conditions into footholds. Blocking silent reuse also benefits from tightening outbound connectivity and external interactions, because persistent attackers often need a reliable way to communicate or extract data. If a function can make outbound connections to any destination, an attacker who controls the function can establish command and control style behavior or can trick the function into sending data to attacker-controlled systems. Hardening does not require you to eliminate outbound connectivity, but it does require you to scope it to what the function needs. This is especially important for functions that handle sensitive data, because any unnecessary outbound path is an unnecessary exfiltration opportunity. Monitoring outbound patterns also matters, because changes in outbound behavior can be one of the earliest signals that a function has been modified or is being abused. Beginners should connect this to earlier lessons about reducing exfiltration risk, because serverless functions can become efficient exfiltration agents if their permissions and network freedom are too broad. When outbound paths are scoped and observed, silent reuse becomes harder to maintain quietly. When an organization suspects serverless persistence or reinfection, the quality of the response depends heavily on whether the environment was hardened for precise containment and clean recovery. If functions have narrowly scoped identities, you can disable or rotate one identity without breaking the whole environment. If triggers are well scoped, you can disable one trigger source to stop malicious execution without shutting down unrelated workflows. If configuration is codified and reviewable, you can compare the current state to the expected baseline and quickly identify unexpected changes. If logs are retained and protected, you can reconstruct the timeline and determine whether a malicious change was introduced through code, through configuration, or through identity. Beginners should notice that hardening is not only about preventing attacks, it is also about making the environment recoverable when attacks happen. A hardened serverless environment gives you a clear path to restore known good behavior and to prevent the same compromise from returning. Finally, hardening serverless functions to block persistence, reinfection, and silent reuse is about reducing the number of durable control points an attacker can manipulate and increasing the visibility of the ones that must exist. You protect code integrity by making updates traceable and reviewable, and you protect deployment integrity by securing the CI/CD path that produces functions. You lock down triggers and event sources so attackers cannot create hidden execution paths or feed malicious events into your workflows. You apply least privilege and unique identities so compromised execution cannot be reused broadly and cannot quietly blend into normal service calls. You restrict control plane permissions for identity and configuration changes so attackers cannot create new footholds through roles and grants. You manage dependencies and shared components deliberately so reinfection cannot spread through the supply path, and you build strong logging and anomaly detection so subtle persistence signals are visible early. When these pieces work together, serverless stays fast and flexible for teams, but it becomes a much harder place for attackers to remain, return, or reuse access without being noticed.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.